So this week we're happy to welcome back Elisa Deutschek, who gave us first talk about the Nancy Grace Roman Space Telescope in November. She has so much information, we didn't get through it all, so she's kindly agreed to come back and give us part 2 of this. So you may remember, but I'll just remind you that Elisa is a principal analyst with the Space Telescope Science Institute. She got her BSc in electrical engineering and a master's in electrical engineering and computer science at the University of Michigan, Ann Arbor, in architecture modeling of complex systems and visual analytics. So please welcome Elisa. And if you have a question, please wait for the microphone because it's going to be recorded on YouTube. And you can also see her first talk on YouTube if you look in the church website. Thank you, Elisa.
Thank you for having me again. So in my November presentation last year, we introduced some concept related to Roman mission. So today I have a presentation 2 parts. One is summarize and update you on the status of Roman mission. And the second part show you some beautiful images from web. And I have videos we just got. Thank you for getting them working, but you know, the video is worth thousands of words, so those are narrated videos. And an extra bonus at the end is how these images are being constructed by 2 members of STSCI team, and they will tell you how they render. Okay, so let's get started. So first slide, please. Second. Oh, okay, I will advance. Sorry. Right. All right. So here is a short summary of Roman mission, key characteristics. Okay, just a snapshot, so that you know when it launches and after initial commissioning period of time, what to expect. So it's 5 years, but we hope for 10 years. You know, Hubble was scheduled for 5 years. Now it's 30 years and still going. So we hope it'll bring us many, many more years. The mission orbit is the same as Webb, which is Lagrange second orbit. Baseline launch vehicle will be launched by SpaceX, and this is Falcon Heavy rocket from Kennedy Space Center in Florida that has been awarded. Okay, launch date is by March 2027. We hope it'll gonna be at the end of 2026. That's what our preparations are, but the sort of drop date is March 2027. The observatory, a couple characteristics, 2.4 meter primary mirror telescope, and 2 instruments, okay, wide field instrument, WFI, and this is a primary instrument, and I'll talk about it, give you some background on that, and it's in infrared wavelength from 0.5 to 2.25 microns. And also it will have experimental instrument which comes from California, and this one is from JPL. This one is called coronoscope, and coronograph, and this one is a technology demonstration project. Data from observatory travels to a network of ground-based international ground stations. So there are some in US, some Australia, Japan, Spain. It is received in cloud, and the cloud, AWS cloud, is called Daphne. And from there, it's picked up by the members of the ground system, and that is MOC, SOC, and SSC. So MOC is Mission Operations Center, SOC is Science Operations Center, and Mission Operations Center is here in Maryland at NASA. SOC Operations Center is at STSCI, so it's Science Operations Center, and SSC is Science Support Center operated by Caltech and IPAC. So those are the partners, okay? 2 instruments I said on the board, wide field instrument, WFI, and then the coronagraph. Okay, next slide. Roman is a big data. I think that's one thing that you have to remember. It's a survey, it's a huge data, so we process the images from the telescope in the cloud, because cloud is elastic enough, it's expensive, but it's elastic enough to allow everybody to receive the data. So big data, and here is Roman over the 5 years will collect 20 petabytes of data. That's compared to 1 petabyte of web data and 0.172 petabyte, which is 172 terabytes of data over 10 years that Hubble collected. So it's a big data, and it requires special processing and special protocols to be able to process the data. Okay, so that's kind of important to remember, and in the slide, the size is supposed to indicate how big data it is. And now about the telescope main instrument, WFI. So it has, I just want to point out some parts on it because I will show you a video which will animate the processing of images of light from the telescope. So 2.5 aperture where light from astronomical objects enters. Main curved mirror, you will notice. Secondary mirror, a series of flat mirrors at various angles. Wheel assembly, which contains 6 filters in different IR region, and focal plane array, which is the difference in this telescope from Webb, is that it has 18 detectors, which convert the light to electric signal, and each image is 300 megapixels. Okay, so that's the components. So let's go to the, okay. I have a video about this. It's really nice to remember because visually you can remember how components.
The Wide Field Instrument is the heart of the Nancy Grace Roman Space Telescope. It is what allows the Roman Space Telescope to take pictures with the same detail as Hubble, but covering an area 100 times larger. Despite this incredible power, the basic design is the same as telescopes around the world. Light enters through Roman's 2.4-meter aperture and is reflected and focused by the curved main mirror, which is also the largest mirror in the telescope. This light is reflected and focused once more by the secondary mirror. More elements tighten the beam and strip it of stray light rays before it passes through the filter wheel. This wheel has a variety of filters that allow different wavelengths of light to pass through. It spins from one to another depending on what the researcher is looking for. Finally, the focused and filtered light reaches the focal plane, where it creates an image on the detectors. These detectors use the photoelectric effect to convert photons into an electrical signal that is then decoded into an image. In Roman's case, there are 18 detectors, allowing it to create 300 million pixel images of large patches of the sky. The large number of detectors and pixels gives Roman its wide field of view. The size of the mirror and the precision of its optics gives Roman its fine imaging. This combination of image size and detail has never been possible on a space-based telescope before and will make the Nancy Grace Roman Space Telescope an indispensable tool in the future.
The next one. Just wanted to show you some just comparison between Roman and Hubble. I think somebody said it's like with Hubble or with Webb, it's like looking through a straw, exactly, you can see there. And this is the size of the images that Roman will send to the ground for processing. The next one is Hubble has been studying galaxies for 30 years, and this is what Roman will be able to do, and that is not only identify Hubble galaxies, but millions of galaxies in its field of view. And the galaxies such as, from top left, spiral, bird spiral, dwarf, elliptical, irregular, elliptical, and lenticular. So astronomers have different names for identifying the galaxies. The second instrument is coronagraph, and it's a technology demonstration project. It will be used to image exoplanets. And exoplanets are planets outside our solar system. They are dim and distant. They orbit around their host stars, which are 1 billion times brighter, so it's very difficult to detect them. By blocking the star's light with coronagraph instrument, the astronomers can image that fainter planets in orbit. You can see the exoplanet at approximately 3 o'clock in the image. Okay, so that's what the coronagraph does. As far as main areas of science, and this has been studied by National Academy of Sciences, there is decadal studies, so measuring dark energy, number one, and that dark energy is 68% of cosmos energy and is attributed to be the cause of universe expansion. Investing in exoplanets, and those exoplanets are of interest because that's where the astronomers will look for habitable Earth-like planets in the future missions. And then contributing to this is a great observatory of astrophysics and contributions to the planetary science. So let's go quickly through some of the community surveys that will happen at the beginning. So Roman is different from other telescope. It is a community-driven mission. In other words, community of astronomers and non-astronomers have formed 3 groups, and these 3 groups defined 3 community surveys. And those surveys basically integrate the science goals, okay, into the surveys. So each community survey is assigned on sky time by the telescope. And you can see that, for example, these are galactic budge time domain surveys. So we've never had the time domain survey, which means for 13 months, the telescope will look at galactic bulge and try to detect transients element. There are lots of transients, things that are happening that just because you point a telescope at the sky, you may miss it. So this will be able to tell us the story, the time domain. a high latitude time domain survey, 6 months. There's high latitude wide area survey for 24 months. And then, of course, there will be after that general astrophysics survey by competition, by submittal of proposals. And the exoplanet coronagraph will have 3 months to demonstrate its technology, okay, ability to. Important thing to note is that all observations will be publicly available with no period of limited access, which is different from current practice. Because for competition, whoever wins the competition, and the competition is from all institutes and astronomers from all over the world, these who win the competition, researchers and their institutions, they have priority over anybody else for research, okay? So this is a new way of organize. Okay, community survey. So first one is galactic bulge time domain survey. So this is our Milky Way has been selected, and it's a view that's the bulge, picture of the bulge. And this will allow us to study the dynamic between formation of stars and dynamics of the heart of the galaxy, of our galaxy. So it's obviously, because it is a function of time, we will be able to track change in brightness to discover distant worlds. Imaging exoplanets is also part of this community survey, and then general astrophysics technologies. Yes. The bulge is that plane. Yeah, if you look at
Is the bulge the center of our galaxy?
The bulge is externalities of the galaxy. Yes. It's a dark area where lots of things are happening. That's what we look in astrophysics, yes. So the second one is high latitude, again, time domain survey. Again, this is revealing the dynamic universe beyond our galaxy. So the first one looked at our galaxy, this one beyond our galaxy. So the same region will be observed every 5 days for 2 years with the survey. And these observations are expected to uncover lots of transient objects that we're not able to study. We saw the after effects of these objects, but they, like exploding stars or stars being swept into black holes and other interesting phenomena, and also imaging with coronagraph. The third study is called Stars by the Billions and Galaxies by the Millions. And basically this middle, we are in this picture, we are on the right side, right? That's where the current is. This is astronomical time. As the galaxies and universe developed from first star to what we have now, and it's expanding. So this will study, basically make a 3D map of the universe and discover all the stars that we haven't been able to discover by looking through a straw, as somebody said, through the sky. So it's phenomenal, right? Here's the comparison of wide area survey with Roman 2,000 square degrees, which will cover 5% of the sky at one time. versus 1.6 square degrees with Hubble, for example. Same with Webb. So we're looking at really a survey. And here's status of Roman telescope. You can find all of the status is reported on NASA website. I give at the end of presentation, I give you the link to NASA Roman telescope, but if you Google, you can get there. So as of January 8, the telescope payload, which is composed of telescope instrument carrier and 2 instruments, which is WFI and coronagraph, they have been integrated successfully into the instrument carrier, completing the Roman payload. So it's a major milestone. This slide shows other milestones, but that is a major milestone. The next step is for this payload to be tested in environmental, to undergo environmental tests, such as electromagnetic, heat, etc. Okay. So that's what I have in summary of the Roman telescope. So it's a big data, okay? It's a survey of the universe. It'll study universe as a function of time. And it's in infrared, which will give us insights into this sky that we haven't had with other instruments. So that's the beauty of the Roman, okay? Now we go into part 2, which is look at Webb images. These are all recent images except the last one, which is from 2022, because it is beautifully narrated by a colleague at STSCI at the Institute. And basically it is a multi-wavelength. It shows you with different telescope what you see, what it means that you see. And finally, the last video is presentation by 2 members of STSCI site who are responsible for producing the beautiful images that you can go and see. And I gave you a link at the end of the presentation where you can look at these images. Okay? So here is the Sombrero Galaxy. Okay, and it is a video. I will say a few words, and then just because I want to prepare you here, there's no narration of this video. But Sombrero Galaxy is named by Hubble astronomers, and because the Hubble is a visual instrument, right? Because visually in Hubble, it looks like a Mexican sombrero, okay? So yeah, astronomers give interesting names to some of the galaxies. So this galaxy also in the catalog is called M104, okay? And there will be 3 images, so you can see the first image is the infrared with NASA Spitzer Space Telescope. The second image shows the Webb telescope image in the mid-infrared. And the final is the Hubble telescope image. And I will, we can maybe play this. There's no audio on this, so if we can play. Yeah, so you see Hubble and Spitzer, Webb, Hubble, Spitzer, Webb, Hubble, Spitzer. Yes. So if we can replay it, but I'll describe what the astronomers found with Webb images that they didn't find. So first of all, they found that in Webb images with infrared, this galaxy, Sombrero Galaxy, didn't look like a Mexican hat sombrero. it looks more like a target, where you shoot at the target. And not only that, but also archery target. Different things, different things that you can see if we go through the images again. The glowing core seen in visible light does not shine like that in Webb's images. Those are smooth inner disk. And the sharp resolution of those rings provides insight into how dust, which is the essential building block for astronomical objects in the universe, is distributed. The outer ring is, so maybe we can play it again. So we can see, this is a Hubble image. It looks like a sombrero. But then if you look at the Spitzer image, it's smooth like blanket in imaging. And in Webb, it shows, those rings show intricate clumps in the infrared for the first time. And astronomers think that those clumps is where stars are formed, young stars. However, they've studied it, however, and determined that unlike other galaxies that Webb, like Messner 82, this galaxy is not particular hotbed for star formation. So they always compare the formation to our Milky Ways. That's the way they look at it. So the rings of the Sombrero Galaxy produce less than 1 solar mass of stars per year, in comparison to Milky Way's roughly 2 solar masses a year. So they're not too excited about this. They will be looking at other areas where there's much more action. And also the supermassive black hole in the center of the galaxy is rather docile, because it is a hefty 9 billion solar masses, so it's huge. It's classified as low luminosity active galactic nucleus, slowly snacking on infalling material from galaxy, while sending off a bright, relatively small jet. Some other galaxies have really dynamic, you will see in some other slide, they have this plume going out from the center, from the nucleus. So I'm going to go to the next slide, please. And this is a very famous because it looks gruesome, right? Those are 2 galaxies on the left, on the right, and we'll have a video about it. I'm just going to set the words up here. And the gruesome view of these galaxies is owed to a mix of mid-infrared light from James Webb and visible and ultraviolet light from NASA Hubble. The pair grazes, so there's a whole narrative which describes the interaction between these galaxies. So the pair grazed one another 1 million years ago. The smallest spiral on the left, catalogued at IC 2163, passed behind NGC 2207, the largest spiral galaxy on the right. And the interactions and all these regions as a result of interaction will be explained in the video. So both increased, the interaction resulted in increase of star formation rates. Combined, they are estimated to form the equivalent of 24 new stars that are the size of a sun annually. That's compared to 2 new sun-like stars in Milky Way. So it's comparable to what happens in our galaxy. So let's advance to the next, and this is a video. And you can see that this is released 2024, so October.
As we zoom through the cosmos, 2 galaxies emerge from the darkness, entwined in a gravitational interplay. On the right, NGC 2207, the larger of the pair, exerts a gravitational pull on its smaller neighbor, IC 2163, seen on the left. Though they haven't yet merged, their close encounter has begun to pull and twist their spiral arms, causing tidal extensions, ethereal tendrils stretching across the void, marking the early stages of their cosmic interaction. These galaxies reside 114 million light-years from Earth, with NGC 2207 spanning 143,000 light-years across, and IC 2163 measuring 101,000 light-years, about the size of our own Milky Way. What makes this image even more spellbinding is the blend of data from 2 powerhouse telescopes. Webb's mid-infrared view captures star formation happening right now, while Hubble's visible and ultraviolet light reveals young stars that have recently burst into life. It's like peering through 2 windows in time, layered together to offer a richer view of these galaxies' evolution. Notice the striking blue clusters scattered throughout the image. These are clusters where stars are forming at a furious pace. Hubble highlights these stellar nurseries, while Webb's mid-infrared vision casts a ghostly red glow, illuminating the dusty regions that envelop the stars. Together, these views give us a haunting look at the galaxies, wrapped in luminous shells of dust. These galaxies are star factories, producing new stars at a rate 5 to 10 times faster than our Milky Way. Each galaxy has witnessed several supernovae, massive cosmic blasts that have left their mark, spreading new elements into space in the process. These powerful explosions may have carved new pathways for fresh star formations, visible as the intense blue patches scattered throughout the image. And those blood-red lines, they're likely shock fronts, zones where the galaxy's materials have collided and compressed, creating a spine-chilling reminder of their turbulent interaction. This spot, known as Feature I, is a hub of rapid star formation on the outer arm of NGC 2207, glowing even more brightly than the galaxy's core. Though it looks dusty and quiet in visible light, it's actually the galaxy's most active area, a mini starburst region where stars form at an astonishing pace, and traces of ancient supernova explosions echo through the cosmic landscape. In a few million years, these galaxies will merge, their fiery cosmic rendezvous culminating in a single stilled galaxy. This image, brought to life by the collaboration of Webb and Hubble, exposes galactic interactions and star formation in chilling detail, offering us a rare glimpse into the universe's dark mysteries.
Roman will not look at it differently. I'm sure that Roman will incorporate the presence of this, but it'll discover many more, and it will look at it over time. That's the difference. Time domain studies, remember those 3. So, okay, we have to go back. Back to slide 20. So, yes, I wanted to show you here why astronomers are absolutely fascinated by and looking for exoplanets. They look because they're looking at the composition of the exoplanet. And here is one of the exoplanets. It's called WSP-39b. There are different types of exoplanets. some are rocky exoplanets, some are gas. This happens to be a hot gas giant. And its star, it circles around its star closer than Mercury orbits the sun. And the atmospheric composition here is detected by Webb, different instruments. Webb has about 4 different instruments, and you have on the same scale for each instrument. And what's important here is to look at what it discovered, what elements, atmospheric elements it discovered for each of the instruments. So at the upper left is the instrument called NIRIS. It shows fingerprints of potassium, water, carbon monoxide. At the upper right, data from NIRCam, which is another instrument, shows a prominent water signature. At lower left, data from NIRSpec indicates water, sulfur dioxide, carbon dioxide, and carbon monoxide. And at lower right, additional NIRSpec data reveals all these molecules as well as sodium. Okay, so we're looking for the atmospheric components that support life. So that's with the spectral analysis. That's why the astronomers are interested in exoplanets. The next NASA telescope is going to be multi-wavelength, so it's going to be visible and IR and X-ray, and it will look for exoplanets. It's called Habitable World Observatory, and it's in the development right now, in the proposal. So we'll look specifically for areas where there could be life. Okay. All right, next one, I wanted to show you another interaction of galaxies that collided hundreds of million years ago, and it's a tour of ARP 107. That's a video. Thank you.
ARP 107 is located 465 million light-years from Earth in the constellation Leo Minor. This image captures a scene that stretches approximately 400,000 light-years across. The spiral galaxy is about 6 times more massive than its elliptical companion. In ARP 107, 2 galaxies are caught in the early stages of a merger. On the left, a smaller elliptical galaxy contrasts with the larger spiral galaxy on the right. Their interaction stems from an off-center collision where the smaller galaxy collided with the spiral from the side several 100 million years ago. These 2 bright regions host ongoing star formation. Galaxy collisions can trigger the formation of new stars when interstellar gases get compressed. The spiral galaxy in ARP 107 has an exceptionally bright core. This brightness is caused in part by the supermassive black hole at its center, which consumes surrounding material like gas and dust. As this material falls inward, it heats up and emits a tremendous amount of energy, making the galaxy's core shine brilliantly. In longer wavelengths, we can observe this bright point source, a clear indication of the black hole's activity as it accretes material. A tenuous bridge stretches between the 2 galaxies, composed of a mix of stars and gas, a result of their interaction. This stream of material was pulled from both galaxies as they interacted, creating a visible link that underscores the intensity of their encounter. This new image from the Webb Space Telescope combines near-infrared and mid-infrared light, but each wavelength was also captured separately. The mid-infrared view highlights the spiral galaxy's bright nucleus, while the bridge of material connecting the galaxies disappears in the mid-infrared. demonstrating how each wavelength offers unique insights into the structure of ARP-107. ARP-107 is compelling because it showcases the dramatic effects of galactic interaction, with a distorted spiral galaxy connected by a bridge of material to another galaxy, providing insights into the processes that drive galaxy evolution. But what is it that astronomers love most about this image? It looks like a smiley face.
I always thought black holes were black, but now I see that they could be extremely luminescent.
That's right. Very violent too. Yeah, black holes, very violent. Yes. Now, this is my favorite video, Stefan's Quintet. It was released in 2023, and it's narrated by my colleague at STSCI, Frank Summers, who also holds public lectures where he invites astronomers from around the world or at STSCI to describe the research. Let me just say a few words and then we'll play this. So visualization explores the galaxy group, Stefan Quintet, but using observations in visible, infrared, and X-ray light. The sequence contrasts NASA Hubble telescope, Spitzer, Webb telescopes, and Chandra X-ray to provide insight across the electromagnetic spectrum. So this will show what each wavelength sees and how to interpret it, and it's just fantastic. I look at it every day almost because it's so exciting. So please.
Deep within the constellation of Pegasus lies a tight grouping of 5 galaxies. Called Stefan's Quintet, this collection showcases different galaxy types and how they can interact in dense environments. Ground-based observations show the galaxy arrangement, and the Hubble Space Telescope captures the fine details. Using infrared light, the Spitzer Space Telescope features cool gas and dust, and the Webb Space Telescope unveils new depth and resolution. The Chandra X-ray Observatory reveals a high-energy component both in and between the galaxies. In 3 dimensions, this spiral galaxy is much closer than the other galaxies. The visible light view shows numerous pink star-forming regions and blue young stars. The infrared view highlights the cool gas and dust amid a diffuse collection of older stars. The more distant galaxies are grouped together. These elliptical galaxies are dominated by older stars and have rounded shapes in both infrared and visible light. This barred spiral galaxy has few star-forming regions and some irregular spiral arms. Its core contains an active supermassive black hole. Energetic material around the black hole blazes brightly in X-rays. More distant material shines in infrared light. A tidal tail provides evidence of an interaction with this nearby galaxy. This small spiral is part of the group and passed near the larger barred spiral several 100 million years ago. This galaxy is undergoing a high-speed collision as it crashes into the group from behind. Its shape features distorted spiral arms and stretched out tails with considerable star formation. This X-ray shocked ridge marks where the galaxy is colliding with the dense gas between the galaxies. A bridge of material that extends in front of the barred spiral galaxy can be seen in X-rays. As bright clouds in infrared light and dark clouds in visible light. An encounter with the distant elliptical may have stretched out the spiral before its current chaotic collision. Stephan's quintet shows several types of galaxies, including some with stretched and distorted shapes that highlight interactions within the group. NASA's great observatories provide multi-wavelength observations that enable diverse insights into this complex, compact group.
There is a question.
I'm trying to get some understanding of magnitude. And so my question is in relation, so it's probably two-part. One, in relation to our galaxy, what is the relative size of these other galaxies that we just looked at?
They are much bigger. They're much bigger, like this one. I would have to look up the paper on this, but that's a good question. I'll pass it along to Michael maybe, but I know that some, there are some. There are galaxies of every size. There are millions of galaxies, millions. So these particular, I would have to go to find out.
And I guess my related question is, do we have any views of our own galaxy similar to those?
Yes, we do. And this Roman will look at this Milky Way galaxy as part of one of the community studies. It will also look inside at the core of this galaxy and at regions, the bulge where the stars are forming. So, yes.
Of course, we're inside our galaxy, so we don't see it from outside like that, but we can still see the Milky Way.
That's right, So I wanted to show you, because when I came to STSCI, I was always fascinated by how these guys create those images, right? And that's the STSCI has SOC, which is Science Operations Center. They process the raw data that comes from the cloud. Remember, it goes through the various stations on the ground, that is sent to the cloud and then picks it up. There are about 7 different levels of processing, and they're processing to processing and reprocessing as calibration data, and they correct for various astronomical phenomena, so that astronomers can have understand how to process it. Because there's so much data, astronomers do not process it, so they can have it. So this video, the last one that I'm going to show you, is by two colleagues, Joe Pasquale and Alyssa Pagan at STSCI. They're both astronomers, but Joe in particular is a photographer in addition to astronomy. And they describe how they get the images from different wavelengths, how they depict it, and from white data that they have to full color. So let's see. It's a wonderful presentation too.
How does this become this? Hi, I'm Joseph D. Pasquale.
And I'm Elisa Pagan.
And we're science visuals developers at the Space Telescope Science Institute, the Mission and Science Operations Center for NASA's James Webb Space Telescope.
Our job is essentially to take the raw images from Webb and extract and highlight the meaningful information by producing color images from the black and white data we receive.
So why do we do this? By composing color images from the data, we can see details that we wouldn't be able to see otherwise.
As science visuals developers, this is what we specialize in and do every day, but it's something that you can do too. A great thing about the Webb Space Telescope is that its observations are available through the Institute's data archive called MAST. You can search for the data, download raw images from Webb, and try composing color images yourself.
In this series, we're going to break down the basics of how and why we take Webb's images from this to this. So follow along with us here and visit webbtelescope.org to dive deeper into the process of how Webb's full color images are made. You're looking at an image of thousands upon thousands of galaxies, billions of years old. This is what Webb images look like before image specialists process them to reveal their contents. Telescopes like Webb are designed with science in mind, and science goals are what drive Webb's observations. But, to our great fortune, this instrument of science also captures the stunning beauty of the cosmos. Before I start working on a Webb image, the data have already gone through a lot. Scientists had to successfully propose to observe the target, which includes a lot of detail, like which filters Webb should use on its cameras. The data then went through a calibration system, developed primarily by scientists and engineers at STSCI, which corrects instrumental effects and extracts useful and accurate information. In order to begin composing color images from this data, we start by downloading the image files from our archive called MAST. Anyone, including you, can search for and download the files by using the target's name or coordinates on the sky. When we first open these images, they may appear black, but they actually contain a huge amount of information. Webb's detectors are so sensitive that they capture more light than our eyes or screens can process. So we need to use certain techniques to bring out the faintest details and make them visible to our eyes while preserving the brightest details. Stretching and compression are one of the ways that we do this. These techniques ensure we highlight the bulk of what was captured in the image. We then refine each piece of data by removing any artifacts or anomalies that might be hiding what's there. Downloading and working with the raw data in this way is exciting. It's kind of like getting a box of puzzle pieces without the picture on the box. And this is only the beginning of the process. Stay tuned for the next video in this series, where we'll dive deeper into the journey of composing color images from Webb data.
While color images of space are incredibly gorgeous to look at, there are so many reasons behind our efforts to visualize Webb's data in color. There are many wavelengths of light around us every day that we can't actually see. The Webb Space Telescope sees infrared light, which is a type of light that's invisible to our eyes. If you wore sophisticated infrared goggles and flew through space, you'd see the universe similar to how Webb does. But since our eyes can't naturally see in infrared, to see what Webb sees, we need to translate the light into visible color. Webb captures multiple images using different filters that detect specific elements or molecules. Then we combine those images to make a composite, assigning different colors to individual images based on the wavelength of light they detect. Just like you would translate a language you don't understand into one that you do, assigning colors this way helps us process the information in a way our eyes can understand. The words are always there, but now we can understand what they're saying. After translating the infrared data to visible color, it's time to consider the aesthetics. We use principles of photography to emphasize certain details and ensure that the image is visually engaging while we work with scientists to ensure we're maintaining the integrity of the original data. Composition is also a big part of this process. Sometimes this just means rotating an image to draw the eye to important info, and sometimes this means cropping images to create a more balanced look. There's no up in space, so our team gets to essentially decide what up looks like for each image we release. Composing color images from Webb's infrared data is a really unique combination of science and art. Similar to composing a symphony, we're carefully balancing each note or each color and scientific detail to create a harmonious, scientifically meaningful, and visually stunning view of the universe.
Webb has two main cameras, NIRCam, the near-infrared camera, and MIRI, the mid-infrared instrument. NIRCam captures shorter wavelengths of infrared light, while MIRI captures longer wavelengths. NIRCam has 29 filters, while MIRI has 9 filters. There are a large number of filter combinations that can appear in a Webb image. We assign colors in chromatic order, blue, green, red, from shortest to longest wavelengths for both of Webb's cameras. We then carefully review what each image contains and decide which filters to keep in the final composite image based on the data quality, science, and overall look. We'll create images from each camera, but we'll often have the opportunity to combine images from both cameras, which can produce stunning results. So there you have it, a brief overview of composing color images from Webb Space Telescope data.
Don't forget, this is all something you can try yourself. You can download raw images from Webb right now and try your hand at assigning color.
This series took us through the highlights, and you can learn more about the actual tools you'll need and the whole process through the resources and info on webbtelescope.org.
Thanks for joining us on this colorful journey.
So, in my last slide, thank you, and here are the links to some of these videos and images. Thank you so much.
Thank you so much. That was brilliant. Any questions? Yes.
This is a matter of time. You showed some images from the Webb telescope, but it hasn't been launched. Those are taken from...
No, Roman hasn't been...
Oh, okay.
Roman hasn't been launched, yes. For Roman, we have simulations. So they simulate because astronomers have to know what to expect. So they simulation. But for Webb, we have images, yes.
Paul?
How will the supergiant telescopes in Chile coming online in a few years complement this and add to the data?
Well, we are managed by AURA, which manages the Chile telescope, and I think it's a ground-based, so it will be part of the it will add to the images of the universe. It's not part of Roman yet.
Is it going to see further back in time than what's out in space? Or?
You know, I don't know details. I don't want to comment. I don't know exactly the details of that, but we can look.
We have a question online.
Yes.
Will Roman reveal the radial density profile of galaxies in much greater detail?
Definitely.
Dark energy absorbed by central black hole or other processes?
Definitely.
I have two questions, actually.
Yeah.
One is that you're looking for transients, things that change, like new supernovae and so on.
With
Roman.
Yes.
So in December, I talked about gravitational wave astronomy and neutrino astronomy. Is there going to be a network of alerts when you see like a supernova that's particularly bright to connect with the neutrino detectors?
I have not. That would be a great idea.
Yeah.
I will ask that of some of the scientists because they would have been
right,
fantastic.
alert network.
Yeah.
The other question was, when you detect an exoplanet with the coronagraph can you get a spectrum of the planet, of those exoplanets?
You have to use the methodology that astronomers have, spectral.
There will be enough.
That's right. It's
yeah.
all part of it, yes.
Right, thank you. Other questions? Well, thank you very much. That was wonderful.
Thank you. Wasn't that fun? Yes. And thank you so much for running the videos. I really appreciate that. Yes, thank you. Definitely. Yes, they will be fantastic. And don't forget, Roman is community-driven, so everybody will get those images, definitely. Thank you.